Hey, conceptual physics students, how about figuring out how to solve all the problems on the extra review worksheet? Here is number 1 with Boppo the Clown, 2 Mylar balloons. The force between them obeys the formula K Q1 Q2 over D squared. So in this circumstance, the only thing we don't know is the force. So we simply will plug in K, which is always 9 times 10 to the 9. Charge number 1, which is 3.0 times 10 to the negative 11 coulombs. Charge number 2, which is 8.0 times 10 to the negative 5 coulombs. And then the distance between them squared. And because the distance between them is 0.50 meters, and we want it in meters, we'll just write 0.50 meters and square that. And you get a force of 1.3 times 10 to the minus 3 newtons. Doesn't seem very big, but 1,000th of a newton is enough to hold a balloon, certainly. All right, number 2. These are hot air balloons. Now, in this case, what we're solving for is how far apart they are. So we would wish the d to not be in the denominator. If you multiply both sides by d squared, then you have, as you see here, the d is in the numerator, and we simply need to get rid of the force. So if I divide both sides by the force, notice how this cancels, and I get d squared equals k q1 q2 over f. Well, of course, we wish to find out what d is, not d squared. So we are going to square root both sides, which means d is equal to the square root of, now let's plug in the numbers, k, which is again 9 times 10 to the 9. Q1, which is 3.0 times 10 to the minus 5. Q2, which is 8.1 times 10 to the minus 2, divided by the force. Oh, sorry, I read that wrong. The charge is actually 3.0 times 10 to the minus 5 squared, because both charges are the same. So let's put a little squared there. And divide by the force, which is 8.1 times 10 to the minus 2. And you get a total distance of 10 meters. That's number 2. Number 3. In number 3, again, the d squared is in the wrong place. We need the d squared to be in the numerator. Now, we want the q by itself. So we will divide both sides of this by k, q1, k, q1. Notice this cancels out that charge, and you get q2 by itself is equal to the force times d squared over k q1. And if you plug those numbers in, you get the charge of 8.4 times 10 to the minus 6 newtons. Number 4, Celeste and her air conditioner. So on number 4, we want to use power equals VI. That's one of our primary formulas for power. And then the voltage is the P divided by the I. Well, the power is 2160 watts, and the current is 9 amps. And so the voltage is 240 volts. The answer to part B is that's much bigger, twice the voltage you usually have when you plug things into the regular outlet at your house. For part C, if she connect it to the usual 120 volt line, look what happens. I equals power over V, 2160 watts over that 120 volts, and that produces 18 amps. And that's much bigger than she could handle on her circuit, and the circuit breaker would flip. Number 5, Valerie. Okay, Valerie is again going to use power equals V times I, so I equals P divided by V. In this case, the power is going to be 120 divided by a voltage the power is actually 1400 watts. 1400 watts over 120 volts is equal to 11.7 amps. Now, the resistance for part so for part B, what's the resistance when they're rolling? And that would be 120 volts over 1.5 amps equals 80 ohms. That's for part B. Now for part C, the power is equal to I times V times I. But notice, I is the same as V over R. Okay, so I could write here V times V over R, and I get power is equal to V squared over R. It's another formula that's very useful many times. And we're almost done. Mrs. Olson, the power is 0.900 kilowatts. The time is 12.0 hours. That gives you 10.8 kilowatt hours. Now the cost is $0.100 per kilowatt hour. We are going to multiply that by the 10.8 kilowatt hours to get $1.08 is what it costs. But you need to take that $1.08 and multiply it by 365 days to get $394.20 for the cost for the year. And that's a whole lot of cost. Thanks.